the beginning, there was darkness, and then bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. Between stars, between galaxies, in the vast majority of space, the temperature reads more than 450 degrees below zero.
The deep freeze of space would turn even the air you breathe into nothing more than solid ice.
Now, far-off frozen places bring strange new mysteries.
The Boomerang or Bowtie Nebula is actually colder than the surrounding space.
Is there life on frozen worlds? And why does the ultimate cold change physics as we know it?
We can take light and slow it down to the speed of a bicycle.
Join us as we travel in search of the lowest temperatures in the universe and the ultimate deep freeze. To appreciate the coldest places in our universe, it's important to remember just how hot all of existence once was. We think of the Big Bang as the ultimate hot event, an excitement of plasma and energy.
When the universe was really hot, it was really without form. There was just radiation and particles all zooming around, turning into each other. The Big Bang was a supremely hot event, roughly 100 million trillion kelvins.
Scientists measure temperature using the Kelvin scale, which begins at absolute zero, the coldest cold we know, a complete lack of atomic movement. On Earth, the average temperature is 288 kelvins, or 59 degrees Fahrenheit. Two different ways of noting the same temperature.
When our universe first formed, it was so hot that not even atoms could exist. The entire universe was nothing except for pure energy. It took 100 seconds for our universe to cool to the point that it was only 1 billion degrees.
For a long time, everything was so hot that everything was divided into subatomic particles, not real traditional atoms the way that we think of matter now.
The universe had to cool down to a sufficiently low temperature that, first of all, atomic nuclei could form, and then neutral atoms could form. So without the universe cooling down to a sufficiently low temperature, we wouldn't exist.
The universe kept cooling until 56,000 years after the Big Bang. It had cooled to 9,000 degrees. And the universe kept cooling until 380,000 years after the Big Bang. Temperatures reached about 3,000 Kelvin. And that was the point at which matter and energy finally parted company.
As temperatures dropped to a level we can start to comprehend, it's important to understand the relationship between heat and temperature. Heat is a measurement of energy transfer. Temperature is action.
One of the easiest ways to think of temperature is as the constant collision of particles. You increase the amount of gas in a room, they start colliding, one particle against another. Like people in a busy crosswalk on a Tokyo rush hour afternoon. As those gas molecules collide one with another, the temperature goes up. And as those people collide one with another, their velocities get transferred, people get bumped forward, their temperature goes up. Now you start removing people. Those collisions, they become less frequent. Nerves become less frayed, the temperature drops. And in the same way, as you remove gas from a room, the collisions become less frequent, and it becomes cooler to experience.
As mankind has spread out over all the lands that make up our home in the universe, areas of extreme cold hold a special fascination.
The coldest temperature ever measured on Earth was measured in Antarctica at over 125 degrees below zero. Dry ice, like the ice in this drink, freezes out at about 109 degrees below zero. So you could have naturally occurring dry ice in the conditions found in Antarctica. It's so cold.
Having found the coldest place on our planet, we now journey to the coldest place in our solar system. And surprisingly, we don't have to go very far. In fact, it's a place where humans have already been.
From what we know today, the coldest place isn't exactly where you'd expect it. The Lunar Reconnaissance Orbiter has detected a temperature of minus 397 degrees Fahrenheit in one of those places where the sun's light never quite reaches. It's actually in the bottom of a crater of our Earth's own moon. As the moon goes around the Earth, it slowly rotates. In fact, it rotates exactly once per time around the planet, allowing us to always see the same face of the moon. But as it goes around, sunlight is never able to reach down into the northern pole or reach up into the southern pole. And craters in those two regions are able to stay in constant shadow because the sunlight simply glances past the edge of the crater but never actually shines inside.
Once scientists discovered the ultra-deep freeze on our own moon, they realized there was another place that could be equally cold, on a planet of fire.
The realization that craters like those on the moon could protect ices from sunlight made us start to realize that it's possible to find ices in craters almost anywhere.
Mercury is the closest planet to the sun, and its sunlit side is incredibly hot, many hundreds of degrees above absolute zero. But there are some parts of Mercury that are perpetually cold, among the coldest places in the solar system.
It's Mercury's tilt, or lack thereof, which keeps its polar craters in a deep freeze.
The tilt of a planet is called its obliquity. Earth is tilted about 23.5 degrees, so our poles see sunlight about 6 months out of the year. On Mercury, the obliquity is almost zero, so at some deep craters at the poles, there are spots that are permanently shadowed and never see sunlight.
Although the solar system gets colder the further you travel from the sun, the icy conditions of the outer planets and moons do not rule out the possibility of life.
Out in the outer edges of our solar system, we see a whole variety of frozen moons orbiting the outer planets. Around Jupiter, Saturn, Uranus, and Neptune are all of these little frozen worlds. And what's amazing is maybe, just maybe, some of them could support life.
Scientists have overwhelming evidence to support the notion that on Jupiter's moon Europa, there is an icy crust overlying a liquid ocean underneath. A common tenet of astrobiology: where there's liquid water, there's the chance for life.
Scientists desperately want, like ice fishermen, to go and dig a hole in the ice and see what life we can pull up. Because it could be that deep in the heart of those oceans of Europa, just like deep in the heart of the Earth's oceans, there's volcanoes that support not just bacteria, but entire colonies of life, seaweeds, sea cucumbers. Life as we know it could exist in the oceans of Europa.
One of Saturn's moons is a bit more active, blasting snow out into space.
Saturn's moon Enceladus has ice geysers, and scientists, in trying to find a mechanism for these geysers, can find no good mechanism that doesn't involve liquid water.
Ice from the erupting geysers on Enceladus is coating nearby moons, making them more reflective. So how did scientists know that frozen places such as Europa and Enceladus were geologically active? The key lies in their smooth surfaces.
When the Voyager spacecraft sent back the first up-close images of Saturn's moon Enceladus, they saw huge regions with no craters. This tells us that whatever craters were there were filled in, they were resurfaced. It tells us this is an active object. Stuff's going on here. The number of craters on a planetary surface, moon, asteroid, planet, tells us about the age of that surface. On Jupiter's moon Callisto, or our own moon, we see a lot of craters telling us we have a very old surface. Just like this ice here. This ice is obviously old ice. It has cuts, it has snow. Obviously, it has not been resurfaced for some time. But there's a solution for that. When planetary scientists talk about resurfacing, this isn't usually what we have in mind. Right here, we can tell the Zamboni has passed. We can tell there's been a resurfacing event. The Zamboni has passed, clearing off the snow, eliminating the grooves. This is just like we see on some of Saturn's moons like Enceladus and Titan, where the fresh ice without craters tells us that we have a young surface.
The cold places in the distant solar system are of extreme interest to scientists.
Studying these outer bodies in our solar system teaches us about what the solar system was composed of in its very initial stages. So these icy bodies represent pristine material that really represents the beginning of our solar system and the building blocks out of which our solar system formed.
3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
Now, a new effort is underway to get a closer look at some of the frozen leftovers from our solar system's formative years.
The New Horizons mission is NASA's latest mission to explore the outer edges of the solar system. It's currently the fastest moving object in the solar system, and in 2015 it will reach the once and former planet Pluto.
But after Pluto, where to? It's a once-in-a-generation opportunity to get a close-up look at frozen objects dating back billions of years. The only problem? Scientists don't yet have a second target for New Horizons. Without one, the probe is speeding at more than 37,000 miles an hour, straight for the icy blackness of deep space. If you want to know how our sun and planets formed, you just might find answers in the deep freeze of the distant solar system. The New Horizons mission to Pluto is expected to provide a wealth of new information about the former planet. But after its rendezvous with Pluto, what else can we learn about the coldest corners of outer space and where we came from? That's where thousands of citizen scientists across the world are hoping to make a difference by finding a frozen needle in a haystack.
The New Horizons mission's destination, after it visits this once and former planet, has yet to be found. And right now, there are scientists around the world using some of the largest telescopes, Subaru, CFHT. They're peering into the region of space where we expect to find the object that will have just the right orbit, that it will move itself into the path of the New Horizons mission. Now, the catch is, we have to find that icy object in the outer solar system by flipping through all these thousands, millions of images.
This is a chance for the general public to be part of the exploration of the coldest zone of the solar system.
This is where we need the public's help. We need everyone with eyes to help us look through all of these images to try and find that piece of ice that New Horizons will visit after it visits Pluto.
All it takes is visiting a website and looking at images, and you could change the course of history.
And that's the amazing thing about this project.
It's expected that this mystery object, whatever it is, and whenever it's found, will likely be cold. Very cold. After all, other Kuiper Belt objects are among the coldest places in our solar system.
As you get further and further away from the sun, its energy is less and less able to keep humans, to keep spacecraft, to keep anything warm. You're down at temperatures around 40 Kelvin. These are temperatures when nitrogen becomes a solid, when carbon dioxide becomes a solid, when all the things we're used to thinking of as the gases in the air around us start to become the ground you walk on. And when we look at Pluto and its surface, what we're seeing is a completely frozen world that sees so little sunlight that the things that we're used to, rivers flowing, a glass of water to drink, they can't exist, because even the air we breathe would freeze out to a solid.
Another world dominated by deep freeze, a far-off trans-Neptunian object named for an Arctic ice goddess, Sedna.
Some objects in the outer solar system, like Sedna, have very eccentric orbits, and they spend the bulk of their time in the solar system's deep freeze. However, when they come close to the sun for a short period of their orbit, like 200 years, they actually develop a very thin, a very tenuous atmosphere. As the planetoid recedes, that atmosphere collapses back to the surface.
Sedna is currently about 3 times Neptune's distance from the sun. And upon closest approach, it's 2.5 times Neptune's distance. Now, when it's farthest away, it's about 33 times Neptune's distance, and a total orbital period is about 11,000 years. So the last time it was this close to the sun was around 9,000 BC.
So how did Sedna end up with such a strange orbit?
Some people initially thought that Sedna got ejected out to where it is by an interaction with Neptune. But since the closest Sedna ever gets to the sun is 2.5 times Neptune's distance, this may be unlikely. Instead, it's possible that a passing star actually dislodged Sedna from where it formed, near Neptune, out to where it is right now. Perhaps even one of the stars in the cluster in which the sun initially is thought to have formed. Sedna may be just the first known object in a whole swarm of other icy bodies that would be the inner part of this Oort cloud that we think exists out there.
When it comes to ice on Earth, we're usually talking about water in its frozen state. But ice in the deep freeze of a place like Sedna doesn't necessarily refer to water.
When most people think of ice, they think of the stuff that comes out of their freezer. But when scientists talk of ices, we're just talking about a chemical transition. We're talking about how you can take sometimes a gas, sometimes a liquid, and drop its temperature, leach out the energy, until the atoms change how they behave and become a solid. In the outer solar system, we find ammonia, cleaning solution, freezes out to a solid. We find methane, natural gas, freezes out to a solid. Dry ice, something that we make in labs here on Earth, our solar system's completely filled with it. To a scientist, ice is just something that is in a different state that readily, when you add heat, becomes either a gas or a liquid. Some ices, like this frozen carbon dioxide, don't go from a solid to a liquid like water. Instead, they go straight into gas. This type of ice is the exact same sort of stuff that makes up part of the composition of Pluto and Eris and many of the other outer worlds in our solar system. When we see a comet, when we see its tail, what we're actually seeing is gases, like the gases coming off of this dry ice that are getting streamed out behind the comet by the sun's radiation. Here on Earth, it's just fun to play with.
In this room, I'm surrounded by blocks of water ice, and indeed, water ice is quite common here on Earth, and even some other places in the solar system like Jupiter's moon Europa. But there are some places that have other kinds of ices. Saturn's moon Triton, for example, has methane and ethane ices on its surface. So water ice is not the only kind of ice that there is.
If you're looking for a variety of ices in one convenient location, check out a comet.
What's exciting about studying comets is that you're seeing the material out of which our whole solar system, including the Earth, was made, flash frozen at an early time in the solar system's evolution.
Many scientists believe comets are responsible for Earth's vast oceans, that eons of comet impacts brought liquid water to Earth's surface. If that's the case, these water-carrying comets are likely responsible for every living thing on the planet. So what's colder, a comet or an asteroid? That's what Travis S. of Cedar Rapids, Iowa, wanted to ask the universe.
Travis, comets are actually colder than asteroids over most of their journey through space. And that's because comets start out from the deep freeze of the solar system. That's really cold out there. Asteroids are always reasonably close to the sun, so they're in general warmer than comets.
Frozen comets, icy asteroids. But what about whole worlds covered in ice and snow? As we continue our search for the coldest places in the universe, how low can we go? And could life survive under the icy surface of a planet wandering between the stars? Cold plays a key role in our universe. It's a preserving medium, a protector against the scattering of life-giving elements such as hydrogen, oxygen, and carbon. The coldest places in our universe may hold answers to fundamental questions about where we came from. So imagine a world where it's always an ice age.
In science fiction, ice planets are common. Hoth, Uropenthe, and who could forget the gone on ice planet Zero?
But here, science fiction may be eclipsed by science fact. Researchers are looking for exoplanets that could really be like Hoth, the ice world from The Empire Strikes Back. Large, rocky, and snow-covered.
Hoth was kind of a realistic depiction of what a planet might be if it's sufficiently covered with water that's then frozen because it's too far from the star. You could have a planet that basically has just a frozen ocean with no land continents sticking out.
It turns out that an all-ice planet is not only realistic, it's happened to Earth several times in our history. Several occasions the Earth has completely frozen over. We call that phase snowball Earth. What happens is that the ice sheet grows. Earth cools, we get more ice. That ice is light, it reflects off sunlight. Earth cools, you get more ice, reflect off more sunlight, more ice, and you get a runaway freeze.
And then something changed and good fractions of it warmed up and the glaciers melted. In fact, you might expect that the Earth should be frozen most of the time. And the reason it's not is that we have a thick atmosphere that retains a lot of the heat. If we didn't have the atmosphere, Earth is at such a great distance from the sun that in fact the water should be frozen.
By 2012, scientists had identified more than 700 extrasolar planets, a number that keeps climbing every year. Many are gas giants, worlds that more closely resemble Jupiter and Saturn than Earth. Detecting smaller snowy worlds is a difficult, but not impossible, task.
Our current detection methods tend to find very large planets very close to their parent stars. As our detection methods grow better, we're likely to find more frozen worlds.
One such world, the planet known as OGLE 2005 BLG 390LB. It's believed to be about 5 times the Earth's size, and according to researchers, could consist of Earth-like rocks and ice.
The distance of this exoplanet from its sun is about the same or maybe a little further than Mars is from our sun. So in our solar system, it would reside between Mars and Jupiter.
This particular exoplanet is interesting in that it has about 5 times Earth's mass. So it's considered a super-Earth, one of the lower mass exoplanets ever found. But its temperature could be only 50 degrees above absolute zero. So this would be an icy, large Earth-like planet.
Another type of exoplanet that's expected to be dark and freezing, rogue planets. These are planets that, for one reason or another, have been hurled from their solar systems, cast off into the icy nothingness between stars.
As far as we know, planets form orbiting stars. They don't have to stay there. Gravity can actually cause planets to get slingshotted out of their solar systems. And this is where you can end up with rogue worlds, not orbiting a star, but instead traveling between them.
Without a star to provide warmth, these planets are likely to be dark, cold, and barren. But cold doesn't mean dead, and many scientists believe that it's quite possible that life could exist under the frozen oceans of a rogue planet, even after 1 billion years of wandering through space.
Once they're far away from the star, they could freeze out and become quite icy. But it's also conjectured that some of them could retain a thick atmosphere, which would then keep the heat trapped in that's created through geothermal processes and radioactive decay within the planet. So not all of them are necessarily completely frozen at their surface.
As our view of the cosmos improves, our estimate of the number of rogue planets keeps climbing.
Recent simulations suggest there may be twice as many rogue planets in the galaxy as there are stars.
So what would happen if a passing star sent Earth spinning out of our solar system? As the entire planet goes rogue, tumbling out into the cold blackness of deep space, would life survive?
If that happened, we'd very quickly radiate away not all our energy, but a lot of it. The oceans would freeze, the atmosphere would become a solid. We'd be left probably dead. But imagine finding that world later on intact with its cities. We don't have to worry about this fate, but a civilization growing up around a binary star, you never know what could happen.
Humans may not be able to survive, but under the sea, the way our water freezes would give life a fighting chance.
One of the things that helps keep fish here on the planet Earth safe is our normal water, our H2O water. When it freezes from the top down, leaving the fish safely protected and swimming beneath the frozen surface. Now, if we go to another world, one experiencing a deep freeze, that alien planet might have ammonia oceans or methane lakes. And those liquids, as they freeze from the bottom all the way up to the surface, leaving any fish living in those frozen lakes flapping around on the surface. And that's not a good place for a fish to be.
If Earth were to become a rogue planet, the life forms we see at the very depths of the ocean in subduction zones where these thermal vents are filling the local ocean with very, very hot water, those life forms would go on like nothing ever happened for millions, maybe billions of years. So it's very possible that in the very depths of an ice planet that's gone rogue, life could exist.
Life could exist on a rogue planet, but not forever. After all, space is very, very cold, and life-giving Earth remains, thankfully, warmer.
We're close to the sun. The typical place in the universe, far from any galaxy or star, has a temperature of only 2.7 degrees above absolute zero. That's the temperature of space itself. Really cold, a really deep freeze.
So what is the coldest naturally occurring place in the universe? It's a place where a simple principle you can test in your home has led to a very big chill. Having explored the role of coldness in our immediate neighborhood, we now embark on a journey to even more frigid places. Astronomers have recently discovered what they think may be the coldest star-like object ever found, a mere 40 light-years away from Earth. It's what's called a Y-class brown dwarf, and according to scientists, the temperature on its surface is about that of a warm spring day.
Just in 2011, we found the coldest white dwarf ever found. And this is an object that's so cool that it's actually cooler than you or I as human beings are. And this is an object that's just 80 degrees Fahrenheit.
Our sun, by comparison, registers at a toasty 10,000 degrees Fahrenheit. So is this brown dwarf a star or not a star?
A brown dwarf is sort of intermediate between a planet and a full-fledged star. It's more massive than even a Jupiter-sized planet, but it's not massive enough to ever have had sustained nuclear fusion in its core. So a true star has nuclear fusion going on for a long, long time. A brown dwarf has nuclear fusion for just a short time.
What brown dwarfs do is they bridge the gap between what we call planets and what we call stars. So brown dwarfs are cool, not only because they're cold, but because they have a lot of exotic stuff going on in them. Because they have such low temperatures, you can actually get clouds in the outer atmospheres of these almost stars. And these can be either icy clouds, or in some cases they can be even iron clouds. So we think that some brown dwarfs actually might have iron rain, where iron condenses out of the atmosphere and rains down into the lower layers. But even with the coolest kinds, you can get ices, much like the ones that we see in the cloudy bands that are on Jupiter, in these almost stars but almost planets.
As we continue to move out into the universe, we get about 400 light-years away from Earth, when suddenly, stars appear to wink out of existence, the temperature drops, and we encounter the inky blackness called Barnard 68.
Barnard 68 is significant because of what you don't see. It's just a black patch. There's no light coming from it, there's no light coming through it. It is a black, opaque spot on the sky.
What was once thought of as a hole in the sky is now known as a dark molecular cloud.
Dark molecular clouds are huge clouds in space of gas and dust, and when we say dust, we mean little chunks of water and silicates not unlike you would sweep off your countertop.
Sunlight, starlight, is only able to penetrate the outermost regions of the gas cloud. As you move deeper and deeper within, this opaque system blocks all the visible wavelengths of light. Only the infrared light is able to make it all the way into the depths of the cloud. And this protects the cloud from heating up, and in fact makes the inside of these clouds one of the most shadowed places and one of the coolest places in the universe.
Not only is Barnard 68 a nippy 16 kelvins at its periphery, as you work your way in, it actually gets colder. This is one cold cloud.
One of the most amazing things about objects like Barnard 68 is that right now they're some of the coldest things in the universe. But all it takes is a shock wave to collapse them down and trigger star formation. And the first stars to form, the largest stars to form, are some of the hottest things in the universe. So in one instant, one of these dark molecular clouds can become the hottest thing around. But the moment before, they were the coolest things in the universe.
Continue our trip, and we've arrived at the coldest place we know of in the universe, approximately 5,000 light-years away from Earth. We are now entering the Boomerang Nebula. This bow-tie-shaped nebula is actually colder than the rest of the universe. It's been chilled by the outflow of gas to approximately negative 458 degrees Fahrenheit, just 1 degree above absolute zero.
The Boomerang Nebula consists of rapidly expanding gases from a dying star. And those gases expand so quickly that they've cooled to a temperature below that of the surrounding space.
And part of the reason that it's able to achieve its extremely low temperature is simply because it's made of expanding gas. An expanding gas, just like the expanding gas in this can, drops in temperature as the gas spreads out over a larger volume. In fact, I'm able to take this everyday drinking water, this room temperature drinking water, and freeze it with the gas coming out of this can. Now, I'm not going to claim that the boomerang has ice, but you can see that a little expanding gas can create one heck of a deep freeze.
Using modern technology, it is possible to create even lower temperatures in a lab. So the true coldest place in the universe may be right here on planet Earth.
In laboratory experiments, we can reach very low temperatures now. In fact, the lowest temperature ever reached is something like 1/2 of a nanokelvin, a billionth of a degree. That's really low.
As the temperature in these experiments approaches absolute zero, weird things start happening to matter. Atoms react to the deep freeze by clumping together in a bizarre form of matter.
This is where the atoms all go into essentially the same state. That is, they behave in a similar way, or even the same way. These are weird, weird substances.
Super cold substances that can even stop light in its tracks.
One of the coolest things we can do is actually stop a beam of light. I know it sounds insane, but we can take a beam of light and be able to slow it down, and then play with it, do whatever you want with it, and then release it again. One of the things that you can do with that is stop it, turn it into an electrical signal, and then re-release it and turn it back into light. And this is really interesting because it has all kinds of practical applications in electronics.
It's just another example of how a really deep freeze seems to transform fundamental properties of the universe. Then again, many scientists believe the universe itself is in for one final fundamental transformation to a permanent state of deep freeze, from which there is no return. The universe is doomed. That's the belief of a number of physicists who study potential endgames for all existence. All of the heat and power that was present at the start of time is slowly, quietly slipping away.
The whole story of the history of the universe starts from the injection of this enormous amount of energy in the Big Bang and watching it dissipate as the universe expands.
A universe that begins with a Big Bang and continues to expand will eventually have an energy shortage, for which there is no solution.
In a sense, the universe is slowly winding down. Kind of like when you wind up the spring in a wind-up toy and you let that toy run for a while. Eventually all the energy gets used up. There's nothing stored in the spring anymore, and you'd have to wind it up again to get it to do something interesting.
These toys have some initial energy, and as they go through their little motions, you're seeing that energy be used up and dissipated. Eventually, these toys will stop. They'll be in their lowest energy state, and there'll be no more possible energy output from them.
Well, once all the stars have died, once all the energy is spread out uniformly in the universe, nothing interesting happens because, like the wind-up toy, it's not wound up. The universe isn't wound up anymore.
But the universe itself is getting larger, expanding, and there is no new energy or heat coming into that system.
If the universe doesn't tear itself apart first, the universe will end as a deep freeze, cold, dark, and depressing.
Suns burn out. Planets are destroyed. Galaxies collide, collapse, ignite, then fall apart. Frozen shells of their former selves. Over hundreds of billions of years, every bit of energy in our universe gets used up, lost to the ever-expanding void, as the entropy of our universe reaches a final, fatal maximum state.
Eventually, it will expand to the point where there will be no heat left in the universe. That means no chemical reactions. That means no biological reactions. What you will see is
the final state of our universe is really just going to look like a whole lot of nothing. Nothing to see here, no black holes, no white dwarf stars, no neutron stars, not even any protons. Just nothing.
In a very cold, dark universe, you could say that this will be the ultimate deep freeze.
But does it have to be that way? Is there anything that could prevent our universe from ending up as a frozen, dark void?
In order to prevent an ultimate death of the universe, gravity or some attractive force like gravity will have to pull back together all the constituents of the universe. Right now, the universe is expanding, and the force of gravity as we measure it isn't enough to pull everything together. But we recognize that we don't even know all the players at work. It's only been the last 20 years that we've even known that dark energy, which is a repulsive force in essence, something that pushes the universe apart, we didn't even know it existed more than about 20 years ago.
But it's conceivable that someday the dark energy that's accelerating the expansion of the universe will become gravitationally attractive. If that's the case, and if there's enough of it, then the universe may halt its expansion and recollapse. We don't know that that'll happen, but it might happen. In that case, the universe will experience a really hot heat death, where all the particles are slamming into all the other particles, high temperatures, stars get destroyed, planets get destroyed. You get a different form of a lifeless universe. One which is hot instead of in the deep freeze.
Still, don't break out the sunscreen yet.
My bet is that the universe will end up in a very low temperature deep freeze, because it seems that the current dark energy might be the type that will continue to accelerate the expansion forever. If that's the case, the temperature of the universe will become arbitrarily close to absolute zero, the ultimate deep freeze.
Cold is a critical ingredient of our universe.
Cold is essential to having the universe that we see, because without a cold spot, energy doesn't flow. You need energy to flow from hot to cold, and it is the flow of energy that leads to all the structures that we see in the universe, including ourselves. So we wouldn't be here if energy weren't trying to flow from hot, concentrated, organized place into the many forms that it can flow into in the universe.
So the next time you feel a winter chill or get hit with a snowball, just remember, if it weren't for cold, you wouldn't be here. And if it's any consolation, you won't be around hundreds of trillions of years from now, when the universe enters its final state of deep freeze.